All right, so this is motion frame of reference, and this is intro, and this is part one. So what we will do is we'll take a look at this. Why are we learning about motion? Motion has so many things going on when you observe it happening, like how fast, how far, what direction, not to mention just to mention a few. So tracking objects in motion, like an asteroid or a hurricane, is very important. We will discuss simulations and in class practice using Pear Deck. We're just doing Nearpod right now. And what you'll end up doing is you can participate in class, use the graph to illustrate, use a simulation, take a quiz, and demonstrate what you know that way. So the first thing I wanted you to take a look at was, how do you know an object is moving? And I'm going to let you guys think about that. But I'm going to move on to the next slide here. And it's a video. I'll play this video for you. Start over again.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
So who's upside down? The person walking or the person with the pipe? Your choice.
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind.
So what is moving? The platform the man is sitting on or the wall? Let you decide.
Behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not.
So why can't we tell if he's not moving? So both these answers are correct. No frame of reference or no wall with grid markings. So we need to have something to show us that the thing is moving. So the wall with the grid markings was our frame of reference. When we don't have it now, then we can't tell.
Not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
So this is an open end. What objects that are fixed to the earth can be used as a frame of reference? Things like trees are fixed to the earth. One example. All right. So motion is the change in position of an object with respect to time. So that shows us what motion is. And we typically describe it in terms of things like velocity, acceleration, displacement, and time. All those things move. So some things like someone standing on the beach and sees a plane fly overhead. You're obviously observing the plane moving above you. You're standing still. Now, if you're on a plane, the plane is moving, but you're still. So it depends on your reference. So you can get up and walk around, but you are in your frame of reference. You're not moving at all. Now the Earth, we observe that the sun moves across the sky from east to west, but the sun isn't moving. It's the Earth's rotation that tells us, that makes the sun change position. Seen from a different perspective, all the planets move with the sun as it travels around in the Milky Way. So the Milky Way moves, so the sun does move, but we see that the sun is stationary. So motion and a frame of reference. Okay, so frame of reference is a system to specify the precise location. We usually use graphs. If you're thinking about movement outside, like I have my grandkids, they love to run. So maybe I'll put a mark on the sidewalk and say, ready, set, go. Or maybe I'll say, run to that tree and back. And that they'll know who won by that. All right. So the person on the cart here says, no, I'm not, I'm still. And the person says, no, you're moving. The cart is moving, but they are not. Okay. So whether or not you are moving depends on your point of view. So that's why they say relative to your point of view. So someone's outside of your reference of the moving cart thinks you're moving, but you are standing still. We feel like we're standing still on the earth, but the earth is rotating and it's moving around the sun. So a reference point is a place where we can have a location on to see if something moves. So we can use a tree. It's not moving, or I can put a mark on the sidewalk. And the position, the separation between the object and the reference point is described as something relative to, in relation to the reference point. So this car moved sometime later, and it's now to the right of the tree. So we can tell that. Now, if it was like an ocean of water and you couldn't see anything, you could not tell, couldn't see the land, you couldn't tell if you were moving at all. It could be just drifting. So let's take a look at the coordinate plane here. Coordinate plane, X and Y, X-axis, Y-axis. Vertical axis is the Y, X-axis is the horizontal axis. And we use coordinates to help us. Now, usually the origin is where we put everything, and that's 0, 0. Our origin is 0, 0. Right? So that's a point. So I put a home base there, or a house. And so this mail truck is at 4, the x coordinate, and 0 up, y axis, 4, 0. And if I were thinking about that, the distance between those would be just 4 units, whatever these units are. Now the car over here is at -4, 3. All right. Now the distance between that, we would have to make a right triangle. Figure this out. Now this is a 3, 4, 5 right triangle if you remember your Pythagorean theorem. So this is a distance of 5. Coordinate system is like a map. The reference point is at the origin, as we said before. And then we can see if something is moved from that point. You can tell what its position. The position is the X and Y points. All right. Now, we're going to go into this. Now, this is a scalar and a vector. Now, a scalar is how we describe something that's in motion. A scalar is a quantity or a number, and we talk about its size or magnitude. So magnitude is size and the number. So speed of the car is a magnitude, and it's just a number, 60 miles an hour, m/ph, miles per hour. Now a vector is a quantity that has both magnitude, so a number, and the direction. So weight is a vector because of gravity. Gravity pulls it down. So we have an arrow, and we might say this is 1. And usually in science, they call this newtons, and that is 1 newton. So we have an arrow pointing in the direction it's moving, and that's how we tell the difference between the two. So let's look at this. All right, so categorize the quantity as either being a vector or a scalar. All right, so remember it's a number only. So this is a scalar, number only. Now see, we have east in here, or we could use an arrow. So that's a vector. North, 5 miles, a vector. Now if it was just the direction, it wouldn't be a vector. Here is 20 degrees Celsius. It's just temperature. That's a scalar. 256 bytes. That's a scalar. And 4,000 calories is a scalar. Just a number. It can have a unit, but if it has the direction in it, then it is a vector. Okay. So what is distance? Distance is a scalar. Distance refers to how much ground was the object had covered. It's the length between 2 points, right? So the length between 2 points, so let's take a look at this, from 0, 0 to 0, 5 is 5 units. And I'm not sure what those boxes represent. They could represent miles, or they could represent meters. And then when we're talking about distance, we're always talking about a positive direction. So this is going from -4 to +4. So there are 4 units here and 4 units here. So it went a distance of 8 units. All right. So distance is the measure of an interval between the two locations measured on the actual path. So here we started at 0 in the start. We went 50 meters, turned around, and went another 30 meters, gave us 80 meters. All right, and I think that's where we're going to stop with this one, I think. Okay, let's do some practice here. Find the distance, and each one of these blocks is 1 kilometer from A to C. So there's 1 kilometer, 2 kilometers, 3, 4, 5, 6, 7, 8. So this is 8 kilometers. And because I'm using this legend here, the legend here is kilometers here. So that's why I'm using that. All right, so the distance between A and F. All right, so we've got, and this is 5 centimeters each. So we got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. All right, I'm going to stop right there, and we'll continue on with that tomorrow.